chapter 15, we're going to continue talking about acids and bases, but now we're particularly going to pay attention to buffered solutions. Back in chapter 14, we were mainly concerned with just acid solutions or just base solutions. But now we're going to talk about if we had a weak acid and then the solution also contains its salt, or a weak base and its salt. So let's consider a solution containing hydrofluoric acid, which the Ka is 7.2 times 10 to the negative 4, and then it also in the solution has its salt, sodium fluoride. When the salt completely dissolves in water, it breaks up completely because it's an ionic compound and we know it's a strong electrolyte. So it breaks up into the sodium ion and the fluorine ion. Well, when it's broken up, there's that equation. When the HF is a weak acid, only slightly dissociated, that means that the HF will mainly stay still together. So the major species in our solution of the HF and the NaF are the hydrofluoric acid, the sodium ion, the fluoride ion, and water, because it's an aqueous solution, and we always forget about the water. So between the sodium fluoride dissociating and the hydrofluoric acid dissociating, the common ion between the two is the fluoride ion, because it's produced by both of them. So now we have to ask ourselves, what effect does the presence of the dissolved sodium fluoride have on the dissociation equilibrium of the hydrofluoric acid? So we're going to compare the two dissociations. So just to review, the dissociation of the acid breaks down into the H plus and the anion. And then we also have, comparing to the original just acid by itself, comparing to the acid with the salt in it. And everything is 1 molar. Well, by Le Chatelier's principle, we would expect that the second solution is driven to the left by the presence of the fluoride ion from the sodium fluoride because, and this is on the next page, you are adding fluoride ions from the NaF, the sodium fluoride. So if you're adding, remember in Le Chatelier's principle, we shift away. So we're shifting towards the reactant to make more reactants. And so this shift is what we call the common ion effect, because it's already involved in the equilibrium reaction. It's a common ion between the two. So the common ion effect is also important in solutions of polyprotic acids, but it's a little bit different. The production of protons by the first dissociation step, remember polyprotic means it's diprotic with 2 protons or triprotic with 3. And when you make the protons from the first step, that's what really is giving you those protons. And so it greatly inhibits the succeeding dissociation steps. These succeeding steps can produce more protons, but they also produce the common ion. So our procedures this chapter, we're going to be calculating very similar to what we've already done in chapter 14. The only important difference to note is that the initial concentration of the anion is not 0 anymore. It's now the concentration of the salt that has that anion. So we're going to see that in example 1. For example 1, the equilibrium concentration of hydrogen ion in a 1 molar hydrofluoric solution is 2.7 times 10 to the negative 2nd molar. And the percent dissociation of hydrofluoric acid is 2.7%. So only 2.7% of the hydrofluoric actually broke up into its ions. So we need to calculate the concentration of the hydrogen ion and the percent dissociation of hydrofluoric acid in a solution that contains 1 molar of the hydrofluoric and 1 molar of the sodium fluoride. So what's located in our solution, we have our hydrofluoric acid, which is only 2.7% dissociated, so it's going to still be in there in its original form. We have the sodium from the sodium fluoride. We have the fluorine ion. And don't forget about everybody's favorite water. Okay. Well, because the fluoride ions will affect the equilibrium of the HF, The sodium doesn't really matter to us because it actually is going to form a strong base, and the water doesn't important right now because we're going to use the Ka, so we're going to be following the acid equation. Okay, so our acid equation for the dissociation, remember, is the acid breaks down into its proton plus its anion, and so then we'll have a Ka value is equal to the hydrogen concentration times the fluoride concentration over the hydrofluoric acid concentration. Okay, well, when we're figuring out what to plug in to solve for X, to figure out our concentration of the H+, we are going to do an ice chart where we know that we have 1 molar of the HF, so that's for our HF concentration. And we have 1 molar NaF. So this is telling us the concentration of the fluoride ion at the beginning, initially. So we're also going to put 1.0 by the fluoride. But we don't have any hydrogen yet. So that's our I line. Next, our C line is our change, and we're going to subtract from the side without 0 and add to the side with 0 to both of them. So at equilibrium, we'll have 1.0 minus X, X, and 1.0 plus X. Since our Ka is very small, we're going to just take off with our assumption. So we'll have 7.2 times 10 to the negative 4 equals, we have X times, and we're taking off the assumptions for now. So times 1.0 over 1.0. So the 1.0's cancel out. So that means that 7.2 times 10 to the negative 4 molar is what X equals, and that is the concentration of the hydrogen ion. So that's part of what we wanted to find. We also want the percent dissociation. So that's the percent dissociated over the initial concentration of the acid. So for a percent, we'll take our X value, our hydrogen ion concentration, over the initial of the HF, which is 1.0, times 100, and our percent dissociation is 0.072%. So, if the original solution dissociated 2.7%, by adding the sodium fluoride, we were able to make sure that even less of the hydrofluoric acid would break apart because of the presence of the fluoride ions from the NaF in the solution. They didn't have to break apart. And so that's why the number is different from the original percentage given in the problem. So that's it for level 67. Our problems for the homework are numbers 9, 22, and 24.